All right, we're going to take a look at what it means to be inverse functions. And I'm going to start algebraically, because we're going to have to look at our two functions algebraically, numerically, and graphically to be able to tell whether they're inverses at this point. So to be an inverse, we already discussed this, it means that one of the functions or equations is going to undo the other one. So every operation will be undone in the other one. So to make sure that we understand what we're doing, we'll start with something small. So for example, if I let f of x be x cubed, since there's only one operation, I can tell then that its inverse will be cube rooting x. So when we're trying to test whether two functions are inverses algebraically, then we would have to plug one into the other. That's what our composition discussion was. So I would have to plug f inverse into f. And so it's going to look like f, so it's going to look like something cubed, and I'm going to plug in f inverse, which is the cube root of x. And what should happen if they truly are inverses is all of the operations would undo each other, and you would be left with just x. Because x went in, all the operations were stripped out, and x will come out. This also has to be true, though, in the other order, meaning you have to plug f of x now into the inverse. So this time it looks like the inverse, which is the cube root of f of x, which is x cubed. They still cancel in this order, and you still get x. So for two functions to be inverses algebraically, then, you have to be able to plug them into one another by composition and have them undo all of the operations. All right, so let's look at these same two functions now. Let's look at them numerically. So I'm going to make a t-table here. The first one will be x and f of x. And remember, this was x cubed. And then my second t-table is going to be x and the inverse. And remember, my inverse was the cube root of x. So I want to try to use some nice numbers where I can look for a pattern. So when I look at the first set, I'm going to try to look at some negatives, 0, and some positives to see if I can see any sort of a pattern when I go look to the other one. So if I cube -2, I get -8. If I cube -1, I get -1. If I cube 0, I get 0. If I cube +1, I get 1. If I cube 2, I get 8. Now because some of these ordered pairs, the x and the y match, I'm going to do one more just to make sure we get a good pattern for the other one. So if I cube 3, I'll get 27. So I have a range of negative numbers, some positive numbers, and 0 for input values. So now I'm going to go over here, and again I want to use some nice numbers because there isn't a number that I can't take the cube root of, but I'm looking for patterns. So I'd really like nice cube roots. So to make it look as much like this table as possible, I'm going to start with negatives and move towards positives. So a nice negative perfect cube root would be -8. And then I would say the cube root of -8 then would be -2. And as I work up towards the positive numbers, the next nice cube root would be -1. And the cube root of -1 then is -1. And then working towards the positives, I'd try 0. The cube root of 0 is 0. And the next nice cube root then is 1. So the cube root of 1 is 1. And then again, 2 has a cube root, but it's not a very nice number. So if I jump to 8, 8 will be the next nice cube root. So the cube root of 8 is 2. And I'll go ahead and jump to 27 because the cube root of 27 is 3. And now if you look at the two tables, because remember we've already proven algebraically that these are inverses, and now we're just looking for patterns. So if you take a look at what happens to each of these ordered pairs, although it's harder to see these middle three, what is happening to us is that the x's and the y's are being swapped. So in this first ordered pair that was -2, -8, it became -8, -2. It's harder to tell here when you're swapping x and y when they match. So these three are here, but they're not as helpful to this particular pattern. But then when I jump down to 2, 8, you'll see it becomes 8, 2. And then 3, 27 becomes 27, 3. So basically our pattern is to swap x and y when you are doing these numerically. So if you're given a set of ordered pairs and asked to find the inverse, then all you need to do is swap the x and y. Now let's look at what happens to those same ordered pairs, these same algebra functions, when we graph them, because there should be a visual pattern as well when we go to graph two inverses. So 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. So I'm just quickly coming up with some graph paper here. Okay. Alright, so let's look at the first function where I'm graphing x cubed. F of x is x cubed. So my first ordered pair is -2 and then down 8. My second ordered pair is -1, -1. And then 0, 0, and then 1, 1. So now you have to be careful because, oops, I'm off the screen. These three look like they're in line, and they're not. I'm going to have to make this a smooth curve because this is a polynomial. And then the last one I'm going to graph is 2 up 8. So what's going to happen then is this will curve upward and then it will curve downward. It would look a little nicer if I had been doing this on real graph paper. Alright, now the second one I want to graph on this same graph so that we can see the visual relationship between a function and its inverse is my inverse of x. My inverse of x here. So my first ordered pair is -8, -2. And then these three ordered pairs match. They're the same as the ones on f of x. And then the last one that I'm going to graph is 8, 2. 27, 3 is way off my graph. So, and again, I want to make something nice and smooth here. And even though I didn't have graph paper here with me, you can still see that there's a visual pattern. That between the green graph and the purple graph, they're mirror images of each other. And so if I draw the mirror, you'll see that the 3 points that they share in common are on the mirror, and that's why they share those 3 points. And this mirror is the equation y is x. So whatever x is, so is y. And that's why we have -1, -1, 0, 0, 1, 1. The next one would be 2, 2, 3, 3, 4, 4. All of those lie on the mirror, not either one of the graphs. But so if I were given, say, the purple graph, then I should be able to draw the green graph by reflecting these points over this line of symmetry here, this axis. So I would take this point and reflect it. I would take this point, the purple point, and reflect it over here until I had mirror images. So again, let's look back, and you can see that algebraically, when you plug one function into the other one, they need to cancel each other out if they are inverses. So you'll just end up with x. And then if you look numerically, your ordered pairs should swap x and y. And what that does visually then is it reflects your graph over the line y equals x.